Hello everyone. I just wanted to take a moment to show you some oxidation reduction reactions, also known as redox reactions. The idea behind redox reactions is it's our third type of chemical reaction, which all chemical reactions can fit into, or so I'm told. So the first type of a reaction that everything can fit into is something called a precipitation reaction. And then we have acid-base reactions, and now we have these redox reactions, okay? So taking all those other categories, those can fit into those three. So here with redox reactions, the idea is this movement of electrons, okay? So something that is oxidized or something that goes through a process called oxidation is something that's going to lose electrons. And we're going to say that is LEO, lose electrons, oxidation, or oxidation is losing, okay? The opposite is if the electrons are lost, them being so reactive, something has to gain them. And that substance is going to be reduced, or it's going to go through a process called reduction. And that substance, that chemical, whatever it may be, is going to gain electrons. So in our mnemonic devices, we're going to say that's GER, where gain electrons is reduction or reduction is gaining. Okay? And again, it has to do with electrons. It's all about movement of electrons. Okay? And these must happen at the same time, as I mentioned previously, because these electrons are so reactive. So in order to do these problems, we must first talk about oxidation numbers. Now here are the rules, okay? You have to know these rules. I can only stress you need to memorize them. So let's talk about these real quick. Number one, any atom in an elemental form has an oxidation number of 0. So for example, if it's just magnesium, that has an oxidation number of 0. And I'll talk about, okay, let's jump back real quick. What is an oxidation number? An oxidation number is the charge that something will have, whether it's gained or lost electrons. Oxidation numbers are slightly related to, I should probably say that the charges, the ionic charges, is related to oxidation numbers, okay? So if you just have magnesium metal, it's Mg that has an oxidation number of 0. Okay, if you have Na, oxidation number of 0. If you have elemental, oh, here we go, F2. Now that's diatomic, but that has an oxidation number of 0. If you have helium, that's a gas, that has an oxidation number of 0. Okay, so anything in its elemental form has an oxidation number of 0. Rule number 2 says monatomic ions have oxidation numbers that are equal to their charges. So let's take a chlorine. That has an oxidation number of 0, but when it becomes chloride, it has an oxidation number of -1, okay? Just like its charge. So this is monoatomic or monatomic, single atomed, okay? Let's take strontium, okay? Strontium, when it loses 2 electrons, it'll be 2 plus. That's also its oxidation number. Let's take lead 4. When it loses 4 electrons, it has an oxidation number of 4 plus. Now, when we take a look at sulfur becoming sulfide, that's the same thing. It must have gained 2 electrons to become S2 plus. So that's its oxidation number. So you're going to want to look for these monatomic ions. Rule number 3 is a smattering of a few things. Fluorine, or I should say, actually that should be fluoride, always has an oxidation number of -1. Oxygen has a negative oxidation number of -2, unless it's in a peroxide form, which we'll talk about that shortly. And then hydrogen has an oxidation number of +1. There is one exception, but we don't see it very often. Okay. The last number, or the last thing, which is probably, I don't want to call it the most important, but it's how everything comes together. The sum of the oxidation numbers. So when I add the oxidation numbers, it must be equal to 0 if it's a neutral compound, or it has to be equal to the charge on that polyatomic ion. Now, before I get into this too much, let me just do some examples and see if we can't figure this all out, okay? So here we go. I got a bunch of these things up here. Let's do an easy one. Let's do this one right here, okay? So sulfur, S8, okay, that's elemental sulfur. That applies the first rule, has an oxidation number of 0. By the way, I'll write the answers up top here, and I'll do the math down below to find those answers down here, okay? Let's look at H2S. Let's look at H2S. So when you take a look at H2S, this one's a little bit more difficult. But what you have here is that you don't have any specific rule for sulfur, but you do have a rule for hydrogen, and that says it's +1 most of the time. Okay? So there's 2 of them. So each hydrogen has a +1 charge. So +1 times 2 is +2. Okay? Well, the charge on this whole thing is 0. So what's the missing number? It's -2. Minus 2 is applied over one single sulfur. So the charge on the sulfur is negative 2. Okay? Here are my answers. What's the oxidation number of H in H2S? It's plus 1. What's the oxidation number of S in H2S? It's minus 2. Okay, moving on. Let's try this SCl2 down here. Okay. Okay, so there's no specific rule for sulfur or for chlorine, okay, chloride, whichever, in this case it would be chlorine. But we do know that sulfur is, chloride is -1 most of the time. Now that is the more electronegative atom. That's another kind of side rule as well. But there's two of them, so -1 times 2 is -2. The whole thing has a charge of 0. This whole thing has a charge of 0. There's no charge out here. So it's 0. So what's the missing number? Plus 2. Sulfur's plus 2. Those are my answers there. Okay. Let's jump over here to P2O5. P2O5. There's no rule for phosphorus, so let's not start there, but there's a rule for oxygen. Oxygen's -2 most of the time, unless it's a peroxide, but we'll get to that later. But now there's 10 of them, okay? There's a charge of -10. Why? Because there's 5 oxygens, and each one of those oxygens has a -2 charge. So 5 times -2 is -10. The whole thing is equal to 0. So what's the missing number here? It's +10. But now here, just be careful. The charge on P is not +10. It's actually +5, because we have to distribute the charge of +10 over 2 phosphoruses. So each phosphorus has a +5 charge. So what's the oxidation state, or what's the oxidation number of phosphorus in P2O5? It's +5. What's the oxidation state or oxidation number of oxygen in P2O5? It's -2. Okay. Another example. Let's jump down here to SNBr4. Actually, let's do this one right here, Na2SO3. Okay. So I don't have a rule for any of these except for oxygen, specifically a rule for oxygen. So let's go with that. It's -2. Okay, so that's -6 for the total. The whole thing is no charge, so it's equal to 0. Now, sulfur, again, no specific rule, but not really a rule for sodium too, but I know that sodium in and of itself is a monatomic ion. And monatomic ions, this is sodium sulfite. So sodium, being a monatomic ion, gets its charge as if it was just a normal ion, and that's +1. But there's 2 of them, so it's +2. So +2 plus what gives me -6, and that would be 4. Okay, so +2 plus 4 minus 6 equals 0. This 4 gets distributed over just a single sulfur, so the oxidation state in sulfur is +4. These are your answers. Okay. Last one on this page. Let's go to this one over here. Again, the only rule that you know is oxygen. It's -14, but it's not equal to 0 anymore. It's equal to the charge that this has, and this whole thing has a charge of -2, or 2 negative. It doesn't matter how you write that for me. So what's the missing number now? The missing number now is +12. So +12 minus 14 gives you -2. So 12 has to be distributed over 2 chromiums. So each chromium has a charge of +6, and there's your answers. Okay? All right, I'm going to leave it at that for now, and we'll move on with this with the next video.